such that PQ is that vector. And so I want to know what is Q. Well, let's see, I'm going to move this vector V over here. And so let's see, we go out 2, well then that'll give me a 2 for Q. We go out 2 and over 3, and then up 4. If I go up 4 from -2, where do I end up? 2, not 6. So several of you got 6 for this. So this has to be a 2. Q is 2, 3, 2. So anyway, when you look at this, when I do PQ, I subtract the x's, so this would be 2 minus 0. I subtract the y's, so it would be 3 minus 0. And I subtract the z's, so that would be 2 minus -2. Yeah, 2, 3, 4. But the thing I'm subtracting is negative. Now, having decided that that's what Q is, now forget about it. Q has nothing to do with part B. So it says find the angle that V makes with the z-axis. So I move this thing over here. And let's see, the y-axis is behind this vector. Okay, I got it a little bit long, so 2. So I just want that angle. And I'm just going to do a dot product again. And for a vector along the z-axis, you couldn't do better than k. Some of you used 4k, that was fine also. But I just used k. Anyhow, what answer did we get for theta? 42. 42 on those. Not everybody had their calculator set to degrees, so if you got a very small angle, then your calculator must have been in radians. Because, 42 degrees, 57 degrees is about 1 radian. So 42 degrees must be about 2/3 of a radian or something like that. So anyway, I'd use K. That's your vector most closely associated with Z. Problem 3. We've got this pyramid problem. The sides are of length 4. But the coordinates don't have any 4s in them. So somebody told me, oh, the A is 4, 4, 0. Well, no, A is 2, 2, 0. So we're, anyway, A, 2, 2, 0. X and Y are both positive there. Now, let's see. I have a hard time drawing this picture. That's why I drew it on the computer. But anyway, so here is this base. And here is the x-axis, no, I'm sorry, the y-axis and the x-axis. So if this is the positive x-axis and this is the positive this is the positive y-axis. No, this is the positive x-axis. So I sort of twisted this around a little bit to make it easier to see. And I can't even copy my own picture. All right. So here we go. Here is A, and here is B, back over here. This total distance is 4, so these coordinates are not 4s. But anyway, over here, this is the positive x, and this is the positive y, and so A has all positive coordinates. Well, the x and y are positive anyway. And here, this is where x is negative, so this would have to be -2, 2, 0. Now, the E is up here somewhere, and it's 0, 0, 5. So there was a whole lot of problem with E. Now, what I want are vectors EA and EB. And again, it's subtraction. So I do, let's see, this was where it starts. So 0 to 2, oh, that's a 2. And 0 to 2, that's a 2. 5 to 0, that's going backwards. So this EA, that's sort of basically pointing down and a little bit out. So the Z coordinate is negative here. So it's 2, 2, negative 5. And I said you could either do IJK or diamond brackets. So there's diamond brackets, and the other one is 2I plus 2J minus 5K. And the other one we got minus 2, 2, minus 5. Now, find an angle. So I want to find angle AEB. And there's a variety of ways to do this. A lot of you just did the dot product again. Great. You didn't have to. You could just do this with geometry. So let's see. So I want this angle across here. That's 2 times this angle across there. So some of you used the tangent function. You said, oh, this distance is 2. And that distance here is not 5. On the z-axis it's 5, but on this one you've got to have out 2, so it's square root of 29. Right? So 2 and 5. And so if you did the arctangent of 2 over root 29, you got that angle, and you double it to get the angle that I want. But don't try to do the arctangent of 4 over, what's this, square root of 33, because this is not a right angle down here. There's the right angle. But anyway, I left the geometry to where you could do it several different ways. And somebody took the arc sine of 2 over root 33. That also works. So this is root 33 right there. Anyway, then also the area of triangle AEB. Again, if you got the vectors, you can just take the cross product of the vectors and take the magnitude of the cross product, and that gives you the area. But on the other hand, why not 1/2 base times height, which I think more people did 1/2 base times height than did cross product. And it was what, 2 times the square root of 29, right? Calculate all the first and second order partial derivatives for this function. Now, first of all, dy dx and dx dy. This is not the x derivative and that's not the y derivative of that function. This would be calculus 1 stuff. But instead, I've got f of xy equals whatever it is, 2xy squared minus x to the 4th. And so I've got a first derivative, and you can use the Leibniz notation, del f del x, or you can use the f sub x notation.
Or the capital D.
Or the capital D, yeah. Some people were doing the capital D. Any of those. So anyhow, this gives me, they bring to x, I get a 2y squared, and then minus 4x cubed. And most everybody got this. Now, dyf, or fy, or del f del y, I get a, oh, some of you left off the y squared on this. Some of you just said, okay, the derivative of 2x is 2, and you just forgot about the y squared. No, you need that. And so similarly, when you do the y derivative, don't forget the x. That's part of it. So I just get 2, well, actually 4 x y. And then what about this? There's your constant, and the derivative of constant is 0. So you can say, oh, it's that thing times 0. Or you could just say it's 0. If it doesn't have y in it, then the y derivative is 0. And then why bother writing the 0? And now some, one or two people are saying, okay, I guess this must be the first derivative. This is the second one, because it's derivative with respect to first variable and derivative with respect to second variable. I'm sorry you thought that way. But it says first order and second order. I think it said first and second order. But anyway, these are both first order. And now I have to go to the second orders. So I need fxx and fyy. But I also need fxy. Not everybody got the fxy. And strictly speaking, of course, there's another one, fyx. But everybody knew it was the same thing. Well, everybody that knew it was there at all knew that it was the same as fxy. So anyway, fxx, this now is a constant, so I don't get that. What I get is minus 12x squared. And here, this one, or actually take fxy, then I have to differentiate that one, I get 4y. If I had done fyx instead, I'd have been looking at the 4xy, and that would have given me 4y. And then this one, fyy, is just 4y. No, I already said 4x, there we go. So then, the tangent plane problem. Now, some of you took second order derivatives on the tangent plane problem, but tangent plane, just like tangent line, is just first derivatives, first ordinary derivatives, and tangent plane is first partial derivatives. So anyway, I've already forgotten what it said. Y cubed plus x squared minus 3y. And I want a slope of a tangent plane, tangent line parallel to the YZ plane. Oh yeah, it wasn't tangent plane, it was tangent line. So anyhow, so tangent line parallel to the YZ plane. All right, that means that x is constant. If I'm holding x constant, I'm doing a y partial. So basically, if this is z equals f of x, y, I just take del f del y, or actually, let's call it f sub y of xy. And that gives me 3y squared, and the x squared is gone. Take a derivative of, take a y derivative of something that just has x, and you get 0. And then minus 3. Now, that's not the slope, because this is variable. Instead, what I need is f sub y at, is it 1 and 2? Yes, it's 1 and 2. So the point on the surface is 1, 2, 3. Right? But now, I'm I'm going out 1 on the x-axis and then 2 to get to here along y. So this is 1, 2, and I'm not even going to write the 0 down there, because this is my domain. It's f of 1, 2 equals 3. Because again, this is f of x, y. It's not f of x, y, z. And so then I just put the 2 in here, and that gives me 3 times 2 squared minus 3, which is 9. So the answer is 9. If I had asked for the tangent plane, and instead I didn't even ask for an equation, all I asked for is the slope, so that's just a number. So this is my answer right there. If I had asked for a tangent plane, then I'd have also calculated the x partial. So fx of xy would be 2x. And so then fx of 1, 2 would be 2. And for my tangent plane, I would have z minus the z coordinate equals 2 times x minus the x coordinate plus 9 times y minus the y coordinate. So if I asked for the tangent plane, that's what it would be. But we haven't really done a whole lot with tangent planes, so I decided I would do that on this example. But anyway, so x slope and y slope. And then the tangent line would be found just by putting x equal to 1. The tangent line parallel to the y-z plane, you just put x equal to 1, and then that's what you get with that slope. Okay. Yeah. So then we have these parametric equations. And I said, well, there it is as in chapter 10. Well, how about as a vector value function? So I just wrote that out for you. Some semesters, when I give this kind of a problem, I'll list the calculus 2 type parameterization, and I'll say, write it as a vector value function, but here I just gave it to you as a vector value function. So R of t equals tangent of t I plus cosine squared of t j. Because what we're looking at is xi plus yj. What point, what xy thing has a parameter value of 0? Well, for that, I just do r of 0. So this is r of 0. Now, first I'm supposed to calculate the derivative, but whatever. So A, r prime of t equals secant squared t. Not everybody is totally comfortable with calculus 1, apparently. Oops, including me. It's a minus. So you don't get minus sine squared. You know, the derivative of the power is not the power of the derivative. And you don't get well, there were several things here, but anyway. The derivative of u squared is 2u du, or sorry, 2u prime. And so here is the 2u right there, and then minus sine t is the u prime. Anyway, b, I say parameter value is 0, that means the t is 0. So if t is 0, where do we substitute that? To get the point, I don't do the derivative, I do the original function. So t is 0, I get x is 0 and y is 1 squared. And of course you could just say, well, it's r of 0, and that would have the I and j in it, right? So that would be basically j. But here's a case where I wouldn't write it that way. I'd write it as an ordered pair. And one reason it says, what point, ordered pair. Well, right here it is. That's the order. And then other direction. Instead of saying, well, here's the parameter value, what's the point? Then instead I say, well, here's the point, what's the parameter value? And so at 1 comma 1/2, well, if the tangent of an angle is 1, then that's probably going to be pi over 4. So anyway, pi over 4. And then put this together with A and find out what the unit tangent vector is at that point. So I just calculate r prime of pi over 4, and what we get is 1, I'm sorry, secant squared. So secant squared is 2 pi, and then minus 2 times 1 over root 2 times another 1 over root 2 gives me that. But that's not the answer. Because I want a unit tangent vector. This gives me a tangent vector, but I got lots of tangent vectors at the same point. So if I've got this curve, the derivative is one tangent vector, but I could double it, or I could take, 2/3 of it, or I could even go with a negative. But I want a unit tangent vector. So that means divided by its magnitude, u will equal 2I minus j over the square root of 5. Then we have some arc lengths. I knew there had to be an arc length problem. It's been a long time on arc length. So I have x equals 1/3 t cubed, y equals t squared, and z equals 2t. And so I want the arc length between these 2 points. So 1/3, 1, and 2, and then I've got 996. These are not the limits of integration here, all right? Because you're probably going to do this as a function of t, so the limits of integration have to be t numbers. This is an x number, a y number, a z number, x number, y number, a z number. What's t? Well, 2t is the z number. So 2t is 2, so t is 1. And 2t is 6, so t is 3. So those are going to be the limits on my interval. And there will be an interval. Some of you tried to give me an arc length without an interval. So anyway, there are 2 ways to do this interval. There are 2 ways to do arc length. You can either use vectors or not use vectors. If you don't use vectors, then you say, all right, the arc length differential is ds equals the square root of dx squared plus dy squared plus dz squared. So then you just need dx, which will be t squared dt, and dy, which is 2t dt, and dz, which is 2 dt. Dx is not t squared, because t squared is not a differential. The differential is t squared times dt. That makes it a differential. All right, well, anyway, so I square and add, and as I do so, I have t to the 4th dt squared plus 4t squared dt squared plus 4 dt squared. I can factor that out. I'm going to get dt times the square root of all of this. And you know what? I rigged the problem. I rigged the problem so that this would come out as an easy square root. Not everybody saw it that way. Some of you said, oh, that's an easy square root because I can do t squared plus 2t plus 2. No. The square root of the sum is not the sum of the square roots. Even in Calculus 3, that doesn't work. It didn't work in algebra. It doesn't work in Cal 3. But I made it to where it would be easily factorable. So that's t squared plus 2 squared. So it's just t squared plus 2 times dt. There it is. And that has an easy integral. So we just integrate that from 1 to 3. And get some appropriate, was it 38 thirds? Is that what it was?
38 thirds, yeah.
I'll leave it to you to work that out. But the other way to do this, instead of working with the differentials, instead of getting your hands real dirty with differentials, what you can do is turn it into a vector value function. And I even wrote it down for you, didn't I? So R of t, yeah, I wrote it down for you, and I said, what we needed was R prime, but take the magnitude. Do a magnitude of a vector, that's the square root of the sum of the squares. So when you take this and work it out, you'll get this square root right here, which simplifies to t squared plus 2. And then ds, I didn't actually write down the magnitude, did I? But anyway, ds is this thing times dt. So you need to know that. And some of you wrote down, magnitude of r prime of t, and then you never took a magnitude. So all right. Y'all did real well on 9, and 8 was not so good. 10, those of you that pushed you through did fine. Some of you just sort of lost hope at some point. Just quit. On 9, there are infinitely many possible answers on 9. So find a specific vector that work, but there are infinitely many that actually work. One very easy one, and y'all gave me quite a variety of good answers. One very easy one, since I want, this is v, and I want v dot w to equal 4. Well, look at that one right there. If I just multiply by 4, 4 times 1, I got 4. So I could just use 4j. Okay. I dot j is 0, j dot j is 1, k dot j is 0. So if I do j dot 4j, I get 4. But there are lots of right answers. And notice on problem 10, that equation there is Laplace's equation. Laplace's equation in 2 space variables. It's hard to say 2 state variables, that's some other part of knowledge there. 2 space variables. The answer is -6. Some of you messed up on number 6 the same way that you messed up on this problem by, let's see, of course, everything got erased here. But when it's when you're taking an x derivative and there is no x in it, then you get 0. You don't get the y stuff. So some of you, in taking the x derivative for the y to the fourth, you just said, oh, I get y to the fourth. No, you don't. You get 0. And then if you mess that one up, it's impossible to get a constant for a. You can get some sleazy variable stuff, but you can't get a constant. I would like to point out one thing about the answer here, -6. So if I find out that a is -6, and that's all I ask for is what's a. But if you put that back in the function, you get x to the fourth minus 6x squared y squared plus y to the fourth. This would be the u thing. And it's kind of remarkable that Laplace's equation, the Laplacian, seems to connect with complex numbers really well. If you take x plus iy, which is basically the variable that you have for complex variables in the plane, x and y. That's all controlled z. Anyway, if I look at z to the fourth, x plus iy to the fourth, and if you know Pascal's triangle, great, otherwise it's a little slower to do this, but what you get is x to the fourth plus 4x cubed iy plus 6 x squared iy squared plus 4x iy cubed plus iy to the fourth. And so, if I do, let's see, the I and the I cubed, that gives me, that just gives me I. Then doesn't give me a real number, it gives me I or minus I. But anyway, this one, I squared, is -1. So that's going to give me a minus 6x squared y squared. And here, I to the fourth is plus 1. So anyway, this solution of the Laplacian is the real part of the fourth power of a complex variable. And if you look at the other part here, plus I times 4x cubed minus 4y cubed. So I cubed is -I, and you factor out the I, you got that. That also is the solution of the Laplacian. Oh, wait a minute, I left out the, this is supposed to be xy cubed, and this is supposed to be x cubed y. Well, the first one was x cubed y, and then there's xy cubed. Anyway, that gives you another solution of the Laplacian right there. And it's the same is true no matter what